So one other quick topic for today. I want to talk about, I mentioned at the beginning this notion of a graph being connected, and so I want to just make that a little bit more precise and show you application of breadth and depth first search. We'll see more, but this is the first one. And now it's important that the graph is undirected. I'll treat the directed case on Thursday. So I want to talk about the notion of connected components. Okay? And so, I think you all know intuitively what these are. They're kind of the pieces of a graph. Right, so for example, you might have a graph with 10 nodes, like so. So this is a graph that evidently has 3 pieces, or 3 connected components. I don't want to belabor this point, but sometimes for proofs, and also just to sort of segue into Thursday's lecture, it's good to have a formal definition. So let me just briefly tell you what that is. So for an undirected graph, what are the connected components really, these pieces? It's the equivalence classes of the equivalence relation, which says that U and V are related. So this is the equivalence relation, this squiggle, if and only if G has a path between them. Okay? So remember, relation is an equivalence relation. It should be reflexive. That's clearly true here. Everything has a path to itself. It should be symmetric. In an undirected graph, this is clearly symmetric. You can get from U to V if and only if you can get from V to U. Transitivity you get just by pasting 2 paths together. And I'll leave it to you to verify. Okay. And if you look at the pieces, it's kind of obvious. Yeah, I can get from, point A to point B anywhere in here, anywhere in here, anywhere in here. Those are the 3 classes. Okay. So let me connect this notion of components to breadth first search. You can use depth first search also, but let me just use breadth first search. So I claim that BFS started at a node S, explores exactly the nodes in the component of S. Okay, so if you started at node number 1 in that graph, BFS will hit nodes 1, 3, 5, 7, and 9, nothing more, nothing less. Okay? And the runtime is proportional to size of component. Okay? One direction of this I think is obvious in the sense that you'd never pick up nodes that were not in the component. Right? All BFS does is explore edges, so if there's no way to get out of the component via an edge, BFS won't find it. Conversely, it will find everything that is in the component. Okay? So proof idea, I'll leave this for you to check. The level I nodes, so for all levels I, the level I nodes of BFS are precisely the nodes at nodes that are I hops away from S. Okay? So I recommend checking this and proving it by induction. Okay? And again, what is the point? So what was the first claim? The first claim is if you start BFS inside a connected component, it's going to find everything in that component and nothing more. The nothing more, I think, is obvious. So the point here is that you don't miss anything. You will not miss anything with BFS in a connected component. This makes that precise. It just says, well, if something's in the connected component, it's some number of hops away, like 17 hops away. So just run for 17 layers and BFS will find it. Okay? So again, the upshot is one invocation of BFS. You will discover everything in that component, and it will take you time linear in the size of that component. So final claim for the day, and this is a very important subroutine in graphs, which is that you can compute all of the connected components in an undirected graph in linear time. Okay? So it's sort of already obvious you could find, say, one piece in linear time. But in fact, for graphs that have many pieces, you can find all the pieces in time linear in the graph. The code is short and sweet. So you do a single pass through the nodes. I'm thinking of the nodes as labeled from 1 to n, just like they are in that upper left corner. When you get to a node, say number 7, you say, have we already explored this? If so, you skip it. If you haven't yet seen node number 7, then you do BFS from I. Okay? So for example, let's evaluate the subroutine on that graph on the upper left. What do? You start at node number 1. Okay? You say, have we seen number 1 before? Well, no, of course not. So you do BFS. What do you discover? You discover exactly nodes 1, 3, 5, 7, and 9. Okay? After that BFS completes from 1, you return to this for loop. You go on to node number 2. You say, have we already seen node number 2? No, we haven't. Well, then BFS starting from 2. That BFS will discover nodes 2 and 4. Okay? Once that BFS from 2 completes, we go to the next iteration of the while loop. I is now 3. Have we seen 3 before? Yes. Okay, we saw that when we were BFSing from 1. We go on to 4. Have we seen 4 before? Yes. We saw that BFSing from 2. Have we seen 5 before? Yes. We saw that BFSing from 1. Have we seen 6 before? No. So finally, we'll call BFS from node 6. We'll discover the last 3 nodes. Okay? So exactly 3 BFSs are called, 1 per component, corresponding to the first time we see a node that lies in that component. Okay? So every component will be discovered eventually, because effectively we do exhaustive search through all of the nodes, so there's no way a component can escape us. We'll see it eventually. And the running time overall, well, there's overhead, which is O of n. That's just because there's n iterations of the while loop and a constant time check for each iteration of the while loop. Plus, we do 1 BFS per component, only 1. Okay, we've already BFSed a component, we find everything, we'll never BFS it again. So, the total runtime in the BFS is 1 BFS per component. Remember, in a given component, BFS runs in time proportional to the size of the component. Now, what is the sum of the component sizes? Well, each node of the graph G lies in exactly 1 connected component. Each edge of the graph G lies in exactly 1 component. Okay? So there's no redundancy. These component sizes are exactly the same as the size of the graph. So this is O of m plus n. So overall, O of m plus n. Okay? So I don't want to run over, so I'll take questions afterwards, but on Thursday we'll talk about a directed variant of connectivity, one of the more clever algorithms we'll see this quarter. See you then.